In chemical reactions, there is a specific speed at which the reactants are used up. The speed in which the reaction occurs is called the rate of the reaction. This rate could be expressed as an equation or more known as the rate law equation. The rate law equation simply states the rate a specific experiment uses up its reactants in constant temperature. In this video, rate law equation and method of initial rates which is used to determine the rate law value from experimentally measured rate data would be discussed. Rate law expression describes how its rates depend on concentrations. Thus, rate law is experimentally deduced for each reaction from a study of how its rates vary with concentration. The rate law expression describes the speed of the reaction with respect to the reactants and its orders at a given temperature. The general form for the rate law is Kaxby, where K is the specific rate constant for the reaction at a particular temperature and X and Y are the orders of the reaction. In these experiments, the temperature is constant and the concentrations of the reactants are changed, which also changes the rate or not change it at all depending on its order. When it is zero order, there is no effect on the initial change on the rate of reaction. So any change in concentration, however big or small it may be, it would not affect the rate. On the first order, initial rate of reaction doubles when the reactant is doubled. So any change done to the concentration would have direct proportionality to the change in rate. Second order, initial rate of reaction quadruples when the reactant is doubled. And the third order, wherein the initial rate of the reaction increases eightfold when the reactant is doubled. The orders may or may not match the coefficients in the balance equation. The orders cannot be predicted. They must be determined experimentally. Another example concerning orders of the reaction is this interpretation, wherein A and B and C are the products with the rate law equation as K, A in the first order, and B in the second order. You may wonder where C went, but it is still there, but its concentrations do not matter because in this example, its order is 0, meaning it does not affect the rate at all. Triple the concentration of A without changing the concentration of B and C, the rate changes by a factor of 3 because A is in the first order. Triple the concentration of B without changing the concentration of A or C increases the rate by a factor of 3 squared, which is 9. Triple the concentration of C without changing the concentration of A or B increases the rate by a factor of 3 raised to 0, which is equal to 1. Important points about K. Number 1. Experimental data must first be used to determine the reaction orders and then the values of K for the reaction at appropriate conditions. Number 2. The units of K is dependent on the overall order of the reaction. Number 3. Unit for K is for a specific reaction which depends on the overall rate of the reaction. Number 4. Value of K does not change with change in concentration by either reactants or products. Number 5. Value of K depends on the presence of a catalyst and its nature. Number 6. Value of K is for a specific temperature and changes with temperature. Number 7. Value of K does not change with time. The general formula for K is K is equal to rate all over AX BYCZ. This could go on depending on the number of reactants in the reaction. The unit for K could be represented as 1 over m raised to the sum of orders minus 1 times second. This example has a balanced equation of 3a plus 2b is equal to 2c plus d. There are 3 experiments with different rates of formation. So, to solve for the values of K in the reaction orders, we need to find which of the experiments have same concentrations for A. As we can see, experiment 1 and 3 has the same concentrations for A. We divide experiment 3 by experiment 1, so it looks like this. Rate 3 all over rate 1 is equal to Ka3x B3y all over Ka1x B1y. Since the K is constant and the A concentration of A on the third experiment and the concentration of A on the first experiment are the same, we remove them from the equation. So, we get rate 3 over rate 1 is equal to B3y over B1y, which, substituting the values, leads us to 2 is equal to 2 raised to y. From this, we can solve that y is equal to 1. Using the orders we found for B, we could use it to get the value of x. So, we use experiment 1 and experiment 2 which looks like rate 2 all over rate 1 is equal to Ka2x b2y all over Ka1x b1y. Since K is constant, we remove it from the equation. And it would end up like A2 all over A1 raised to the x power and B2 over B1 raised to 1 since y is equal to 1. Substituting values, we get that 24 is equal to 2 raised to x times 3. Dividing both sides by 3, we get 8 is equal to 2 raised to x. From this, we can say that x is equal to 3 and the rate is equal to Ka3b. But we're not done yet. We need to find the value of k. In computing for k, we know that rate is equal to Ka3b. Using experiment 2, we know that rate 2 is equal to Ka2 to the third power b2. Substituting the values, we get that k is equal to 600,000. So the unit for rate is m per second. Unit for a and b is m. What do we need to multiply to m raised to the fourth power so that it would be m per second? It is 1 over m cubed second. So k is equal to 600,000 over m cubed second. This is the last example for this video and there are 4 experiments. So the first step we need to do is to find two values with the same concentrations from one another. Experiment 1 and experiment 4 has the same values for A and B. So we use experiment 1 and experiment 4. Rate 1 all over rate 4 is equal to Ka1x B1y C1z all over Ka4x B4y C4z. Since K is constant, A1 and A4 is the same, B1 and B4 is also the same, we could cancel them. Substituting the values, we could say that 1 is equal to 1 half z. From this, we could say that z is in the 0 order. Because z is in the 0 order, we could disregard its values. So, let's find another one which has the same concentrations for A and B, disregarding C. Experiments 1 and 3 has the same value for the concentration of A. We use experiment 1 and experiment 3. Rate 1 all over rate 3 is equal to Ka1x B1y all over Ka3x B3y. Since K is constant and A1 and A3 are the same, we could cancel them. Substituting the values, we could get that 1 half is equal to 1 half y. From this, we could say that y is equal to 1. To find the value of x, we use experiment 1 and experiment 2 because they have the same concentrations of B. Rate 1 all over rate 2 is equal to Ka1x B1y all over Ka2x B2y. Substituting the values, we get 1/4 is equal to 1 half x. X is equal to 2 and the rate is equal to Ka2 B1 C0. But we could just remove C because its order is 0. So the rate could be expressed as Ka2 B1. So using experiment 1, we know that the rate 1 is equal to Ka1 squared B1 times C0. Solving for K, we can say that rate 1 is equal to A1 squared B1. Substituting the values, we could get that K is equal to 800. The unit for the rate is m per second, so what should be the unit that should be multiplied to m3 so that the final unit is m per second is 1 over m squared second. So we could say that K is equal to 800 over m squared seconds. Thank you for watching. Hit subscribe, hit the like button, and leave comments for clarifications and other questions concerning the topic. Thank you.